Thank you very much. I'm really glad to be here. Thanks for organising JuliaCon in Paris. This has been wonderful. I've had a great time so far. So yes, I'm going to talk about Mooncake. So I'm Will Tebbutt. I'm at the Alan Turing Institute, and myself and Hong at the University of Cambridge, also at the ATI, started this project a couple of years ago. I was also at Cambridge at the time, so a good chunk of this work was done there. So it's the two of us initially, and over time we've recruited various more people. Guillaume has contributed quite substantially. He's the reason we have forward mode AD. And various other people. One person I wanted to give a shout out to was Xianda, who's one of Hong's PhD students, who has helped us a lot. And there's, as I say, there's many more people. You can look at the contributors page to see. There's several in the room as well. So it's very convenient that we just had the talk we had, because I don't have to explain various things. So yes, the recommended way to use Mooncake is to use differentiation interface. So we would import differentiation interface, import Mooncake, then set the backend to be Mooncake, do some gradient preparation. This is where all the compilation stuff happens. This is where Mooncake takes your program f and your argument x, looks up the IR for it, and spits out a new program and transforms that IR to spit out a new program that will do reverse mode AD or forward mode AD for you, depending on what you're after. So yeah, so we do this gradient preparation step once, and then once we have the result of that, we can compute the value and gradient reasonably efficiently, fingers crossed, most of the time. And the idea is you do this prepare gradient step once, and then repeat value and gradient many times if you're doing some kind of optimization procedure or approximate Bayesian inference or something. So I thought I'd start with getting some basic timings out of the way. They're incredibly hard to do. They're all caveated with your numbers will vary on your machine. If you picked a different example, you'd get different numbers. But I wanted to take a very simple Julia function. So I think this is a fairly simple kind of MapReduce example. We're just going to sum over the elements in X, do a little bit of work at each iteration, just compute the exponentiate and compute the cosine of the value of xn, and then add it to the running total. I'm not sure this is the best way to do a MapReduce, as I learned yesterday, but anyway, so it's a simple Julia program. This will run quite quickly, it'll infer nicely and everything. And so if we apply this function to a vector of length 1024 and try out various different AD backends in reverse mode, what performance do we get? So that this ratio column is that gives us the performance numbers, and so this ratio is the ratio of the time it takes to compute the value and the gradient of f at x, divided by the time it takes to just compute f. And so you can see the enzyme and Mooncake get numbers that are below 3. Reverse diff gets a slightly higher number. This is reverse diff in its compiled mode, for those in the know. This is kind of the fastest it can be. And zygote gets quite a bit larger number. And the one thing I wanted to note also here is that so these frameworks at the bottom, they're written in Julia and they operate on Julia IR or just operate on Julia. Enzyme, so it's got its Julia front end. There's a lot of, I think, C++ used to manipulate LLVM. So before moving on, I just wanted to have another example where enzyme gets better numbers than Mooncake in terms of performance. So in this example, we have a slightly cheaper thing inside the loop, and we can see all the ratios are a bit larger, but enzyme has won here. So the claim I'm reasonably willing to make is, generally speaking, if you've written a fast function, such as f here, it'll infer nicely and everything. Mooncake will tend to give you gradients more quickly than reverse diff and zygote, and enzyme will often be faster than Mooncake, sometimes not, sometimes will be. But certainly I would not try and claim that Mooncake is faster than enzyme. But it is faster than the other frameworks in Julia that I'm comparing to here. So as I say, you could pick one of 100 other examples, and in some cases, other frameworks will be faster or slower. Okay, so with benchmarking out the way, why did we do this? So my basic motivation for this was I wanted to have a framework written in Julia that resolved some issues that we had with the reverse different enzyme. Reverse different zygote, sorry, which are, I think, are still issues with those frameworks. I wanted to produce something that I thought was actually testable, and I'll get onto what I mean by that in a moment. And in that vein, one that had good composition properties is maybe a better word than guarantees, but the kind of the errors that you don't want to get when you're doing AD is an error where your original program runs fine, and then you try and AD it, and the AD framework gives you back an error that has happened in some internal thing down in some automatically generated code. It's very impenetrable, those kinds of errors. If you're an expert AD user or a developer like myself, it's equally as impenetrable as it is for users who are less familiar with these things. You really want to have the property that if your original program is fast, you'll get good AD performance. That's the thing we'd like to give to users. And we don't have that with Zygote in many cases. And I also wanted to have wider language support than these other frameworks offered. Of particular note is mutation, so the ability to differentiate code that write to arrays, write to mutable structs, that kind of stuff. So before diving into how we do these things, I'll do a quick AD recap, which happily isn't required to a great extent. But just to set up how I'm going to be phrasing things. So if we're going to assume we have some function f that's differentiable at a point x, we'll just assume we're mapping between two real-valued vectors. It's Jacobian, as we discussed, it's some matrix of partial derivatives. And forward mode is the thing that gives you the linear operator to compute j x dot for some x dot, which is a vector of the same length as the argument to f. And reverse mode, phrase it slightly differently, will give you the linear operator that is multiply y bar by the Jacobian transpose for some vector y bar. And again, like the way that this works is we just repeatedly apply the chain rule over and over again. So if we have a function f that is a composition of f2 and f1, its Jacobian is the multiplication of the two Jacobians. And so we can do forward mode by just composing these operators we discussed on the previous slide, and applying this one, and then applying this one to the result is where you tend to actually implement it. And reverse mode is slightly more complicated. It splits into two phases. On the forwards pass of reverse mode, you construct and store these operators. That's kind of morally what's going on. And then on the reverse pass, you apply them in the reverse order. And the crucial thing here is that you have to store these operators on the forward pass, and then have them available on the reverse pass. And this is where the increased memory footprint of reverse mode comes from. So now that I've got that out of the way, I can talk about testability and the tangent system that we have in Mooncake. So sticking with the same setup we had before, if someone gives you a tool and says, this will compute gradients or do forward mode or reverse mode AD for you, you would typically want to check that it actually does that correctly. And the way that you would do that is usually by computing these kinds of inner products. So you can see on the left here, jx dot is the thing that forward mode would compute for you. It's also the thing that finite differences will give you. And if you just pick some random vector y bar, it doesn't matter what it is, and compute this inner product. So you could test whether forward mode is correct by computing this quantity using forward mode and computing it using finite differences. But the way to test if your reverse mode AD is doing the correct thing is to compute this inner product, which ought to be the same thing. So you use reverse mode to compute j transpose y bar, and then take the inner product with x dot. So if you want to have a general AD system that you can test for any arguments you might want to consider, you need to be really, really confident that you can actually evaluate this inner product and that it's defined on the computer programs and the arguments that you're interested in. And so the system we have in Mooncake is we have this tangent type system where for every type of argument that you might pass into a program, call it this type P in this case, dx or x dot must be of type tangent type P. We define a function called tangent type, and it must be of that type. And what that means is that it's completely predictable what kind of thing you're going to have to compute inner products between is going to be if you know the primal type. And so the system we've constructed in Mooncake, we make absolutely sure that the types returned by tangent type have this inner product defined on them, which isn't the case for any type in Julia, right? If I just give you some type, it's not clear that it'll have an inner product defined. We have to do a few other things in order to be able to implement finite differencing on our tangent system. And the point is we're really thorough with this to the extent that, so we have this function test rule, where you give it a random number generator, you give it the function you're interested in and the arguments, and it will test that AD gives you the right answer for those values. And this will literally just generate arbitrary x dots and y bars of the correct type and test that you get the right number out for you. And this is like our definition of correctness. And so one of the reasons in which this is important in comparison to, say, Zygote or chain rules being the backend that Zygote uses for a lot of its implementations of rules for differentiating things. That system has a very laissez-faire approach to what am I allowed to use to represent the tangent of a thing. And it essentially says you can use what you like. And that makes it very hard to have a thorough testing of your system, because for a given f and x, you're never quite sure whether you've actually tested all the possible types of things you need to test, essentially. And so in Mooncake, we really collapse the space of possibilities, and it makes it much easier to test everything. And so this leads on to the composition property I wanted, which is if I have some program f that say it's a composition of two functions, it returns a value t, and then you pass t to f2. The way that you would implement, morally speaking, implement forward mode AD for this kind of thing is you'd write a function called a rule, or the way we do it anyway, that maps from your function f and the value x and a tangent dx, and then recurses. So it'll apply the rule to f1 and x and dx, and that'll give you t and dt back. And then you'll pass t and dt to the rule for f2, and that'll be your answer. And the thing that really absolutely must work here is that you can pass t and dt to this second thing, provided that you can pass t to f2. And if you can do that reliably, you can be pretty sure that you have the promise, if f runs, then rule of f will run. And so how do we actually achieve this in practice? Well, what you'd like to be able to do is write a rule that applies to f1, completely independently of writing a rule that applies to f2, and just know that they'll be able to compose when they eventually meet. And so by restricting the type of dt to be tangent type t, what it means is that we can much more thoroughly test the rule for f1. We can make sure that it always returns the correct type, because we know that there is one correct type that you must return. And when you're writing the rule for f2, you know that you are definitely going to receive a type of a tangent of type dt, and anything else is an error, and it's not your fault. And so so this caused issues in Zygote again, because this wasn't formalized. dt could be anything. Often it was one of a small handful of things, or typically maybe one thing. But the way this tends to manifest itself is you're trying to differentiate some rather large program. You get some error way down in the computation. You get a massive long stack trace, and it's very hard to figure out exactly what caused the problem. So I've illustrated this for forward mode, but it's kind of, you just get a more complicated and worse version of this in reverse mode if it goes wrong. Essentially, the code you have to produce to do reverse mode is more complicated, and it's harder to decipher when things go wrong. So performance, we discussed that briefly at the top. And the main thing I'm going to do here is talk about the IR that we manipulate. So I've nicked this figure from the Julia language docs. I'm sure you're all very familiar with it. So we intercept the IR around here. We use the Julia IR code type, which is not quite what you get from code types, but nearly. Enzyme intercepts the LLVM IR, and zygote intercepts kind of up here somewhere. And the crucial thing that we get by using the IR code that appears after optimization and inference is we get the types of everything. And so recall at the start I said that for reverse mode AD, you need to be able to store information on the forward pass and recover it on the reverse pass. And so what data structure are we going to use to store that data? Let's say we're going to just push things onto a vector. If you don't have any type information when you're deriving your rules for AD, you essentially have to have a vector any to store all of your information. You have to use a completely untyped container because it might have anything. And so the thing that we gain and so that's what the situation zygote was in, because it didn't have type information. We put ourselves in a slightly better situation because we have type information. What we can do is we can get this nice conditional performance guarantee that's essentially, well, if you know all the types, if you wrote good type stable code, we know exactly what types of things we're going to need to store on the forward pass, and we therefore can create containers that have the correct element type. So for example, if you needed to store a couple of float 64s for the rule for cos, then we can get that information and we can have a vector that has tuples of float 64s in. And so this has been known about for a long time. Mike, when he was writing Zygote, I'm pretty sure was aware of this. The issue was at the time he didn't have the infrastructure available to do this in the way he would have liked. And we now have this opaque closure mechanism in Julia, which is the opaque closures. You can use them to take some IR that you've generated, you put it in it, and it will run it for you and compile it for you. So we can actually do code generation in a way that we weren't able to when Mike was doing it, at least as I understand it. So mutation. So this is one of the big things I wanted to get to work. And I'm not going to go into the kind of technical details of exactly how we implement this, but what I do want to do is explain the mental model that you need to actually make sense of it. So if someone gives you a function like this, where you scale all of the elements of the argument x by 5 and just write them and do that in place, and then return, say, sign of the first element or something, doesn't really matter what. In order to make any sense of this whatsoever, you do need to find a differentiable function that you can associate to f. We don't do maths on Julia code. We need a differentiable function that's defined on the reals. And so the question is, what is this? And the central trick, which is not of my invention, there's this great paper from Perlmutter and Siskin from 2008 entitled Lambda, the Ultimate Backpropagator, that covers this a bit. It's probably known before that as well. I'm not exactly sure what the first reference is. But you should think of a Julia function, or I'm going to call it a procedure. You should think of a procedure as a transition operator that maps from the state of everything before you run the function, the procedure, to the state of everything after you run it, and also the value it returns. And so this function, I've called it phi here. This is the thing that's the differentiable object, mathematical object that you can sensibly do calculus on. So the process of figuring out what it means to differentiate this is to first figure out what this operator is, just do calculus on this, and then figure out how to implement that on a computer. And so in addition to having to just differentiate this, we have a system in Mooncake where on the forward pass you do the regular computation, store some things, and then on the reverse pass you have to undo the changes you make on the forward pass and various other things. It's laid out in the docs in some depth. But the kind of point here is we can make perfectly good sense of this kind of function and figure out what differentiable function it corresponds to. And again, the thing I want to emphasize here is that it's not that you necessarily want to write functions like this yourself. It's that if you're differentiating someone else's code that you don't have control over and you encounter something like this, it would be very, very nice if your AD system didn't fall over. If you're writing code yourself, you can just make it so that it doesn't do any mutation. But there's plenty of code in the wild that does mutate things. So just continuing on the kinds of things we support, just to give you a final overview of this. So all of these frameworks will do something, will differentiate something like this for you with no trouble. It's nice and abstractly typed. It calls out to a function, the Julia function sum, for which all of these frameworks will have handwritten. Well, no, certainly reverse diff and zygote have handwritten rules for sum. I think we do as well in Mooncake. So they'll differentiate this fine. If we consider just a slightly different example that involves mutation, zygote won't be able to handle it. So here we're just updating the value of x in this function. I'm iterating over all the elements. Reverse diff will be able to handle this in general. But then if we were to do something innocuous like restrict the element type, reverse diff won't be able to handle it. And so the list of things that I want to say that Mooncake can do, in addition to those two basic things, is it can handle kind of arbitrarily complicated Julia types, almost. Certainly, it can do things like it can handle incomplete initialization, either as incompletely initialized arguments, or if you encounter some incompletely initialized data going as you're differentiating something. It can handle self-referential data structures. So if you've got a data structure with a pointer to some other bit of the data structure, like a doubly linked list or something. It can do dynamic dispatch. It can do value-dependent control flow. So if you've got a function that is if x is greater than 0, cos, otherwise sine, that's fine. Like BLAS and LAPACK support are a question of writing rules. We have many of them. More will be wonderful. We can handle structured matrices. We can handle callable structs and closures and stuff like that. So I just want to give you a flavor here of kind of the type of generality that we have in Mooncake. So what can't we do? So there's some things that I think we just basically can't do, as in we won't be able to do. It's not a question of how much effort we put into it. I just don't think we'll be able to do them. So there's some forms of exception handling. For those in the know, anything involving epsilon nodes or phi c nodes, they cause real trouble. And I'm happy to chat to anyone who wants to know more about that and why they cause trouble. Things like foreign calls, so calls out to like C code or Fortran code, we just can't do. It's a Julia framework. Enzyme might be able to do it. You have to write a handwritten rule to say how to differentiate a function that calls out to a foreign call. I'm happy to talk about higher memory usage. This is associated to mutation. Enzyme has some optimizations that can partially deal with some of the issues that this introduces. But yeah, I'd love to chat to anyone who's interested in this. And one slightly annoying thing that I've not figured out how to do, and I don't think we can do, is handle self-referential types in an automatic fashion. So if you have a type F and it refers to itself in the type definition, I can't implement a method of tangent type that just works for this, because we can't deal with this recursion. And I think that is essentially to do with the fact that you can't define types on the fly in Julia. Again, if you have ideas on that, I'd love to hear them. So current things that we don't really do right. The code we generate gets in the way of SIMD, which is kind of annoying. Various suboptimal storage strategies for stuff that we store on the forward pass that we'd like to recover on the reverse pass. We don't take advantage of loop invariants, induction variables, various constants, etc. And I'd very much like to do that with some additional analysis. And I have some thoughts on this in issue 156 on the Mooncake repo if you're interested. So, to conclude, various challenges remain. I think that what Mooncake offers does address some of the limitations we had in reverse diff and zygote. And so I think, to my mind, it constitutes progress there. And it's written in and operates on Julia, which is very convenient for those of us who like writing Julia and understand that. Thank you.
Thanks, Will. We'll take a few questions. Just Bushra, are you here? Yeah, you'll actually give your talk in the other room, so don't get prepared right now. We'll switch all of us to the other room to the final stretch. Chris and then Lilith.
So you do say it's written and operates on Julia, right? But there's the caveat, right, that it's using the part of the compiler, plugin infrastructure that isn't quite documented. And I think that you might be the first person outside of the compiler team who's actually figured out how to use it. I would love to learn how to use it. Are you going to be writing tutorials on how to use this and then how to teach it, or what's the way to get other people in here? Because I think in order to really kind of work on and learn Mooncake, you kind of got to start to use it, right? So what's the path to get other people to write such compiler plugins?
Really great question. So to my mind, there are two things. So we have like some introductory docs in Mooncake. They could be better. I think so. The way I work with this is there's a couple of places that I was told at some point by Frames, oh yeah, go and look over here. That might be where you'll find some useful functionality. And so I followed what she said and found useful bits of the compiler, and I just try and roughly track what's going on over time. Of course, it changes because it's internals. So I think there's kind of two things. Either we can try and document those changes fairly reliably or try and have some docs that are kept up to date as to, so you want to do code gen at the IR level, here's what you need to know. And maybe add more documentation to types in the compiler that are quite unlikely to change very much, because obviously you need to trade off between how much time you're spending doing docs for the compiler, or if I was writing stuff about what I happen to know about that might well be wrong, and then getting other people to review it, and I wouldn't want to use too much of their time. You want to trade off between what you write docs for in terms of how fast it's moving and how much effort you put into it. So there's that, and then if there are stable interfaces that can pop out. I mean, I know people have been asking about this for a long time. That would be wonderful. I'm not going to. I'll ask very politely, is it possible we could have a nice stable interface for some of these things? But I fully appreciate that the compiler internals move quickly and things need to change on a regular basis. And so I'm not disappointed that we don't have stable interfaces internally. So I think a bit more documentation that various people could write. I should probably write some more. That's probably the best way in. Yeah.
When should I use Mooncake instead of Enzyme?
When should you use Mooncake instead of Enzyme? That's a great question. The short answer is when Enzyme doesn't run. All of these frameworks will succeed in differentiating different bits of code. I mean, there's stuff Mooncake will fall over on that I'm sure Enzyme doesn't, and I'm reasonably confident in saying there's bits of code Enzyme will fall over on that Mooncake won't. It's just the way these things tend to go. So it's just another option that you can reach for.
Thank you.
We have time for one last question. Yeah, Adrian.
Yeah, thank you for the talk. So regarding mutation, you mentioned undoing changes. So I was wondering what you mean by that.
Yeah. So going back to this function here. So on the forward pass, we multiplied all the elements of x by 5. There's a couple of ways of this is like an implementation detail. It's not something you have to do. I don't think Enzyme does it this way. On the reverse pass, we insist that you restore the original values that were in X. And you can either do that, if the operation happens to be invertible, you can do that given the resulting state. But if you don't have that property, then you just have to store the value associated to X before you update it and then write it back on the reverse pass.